All right, I've got another example of magnetic circuits here, and if you've been watching the previous examples, you know that I love magnetic circuits. I think it's such a great idea to apply circuit analysis to magnetic fields. And I've got a nice little drawing here, and it took me several hours to make that drawing because I'm a bad artist. But anyway, so I've got the drawing ready to go. Here's the example. For this magnetic system, calculate the current in the coil in blue there that will produce a magnetic flux density of 1.5 Tesla in the air gap. So there's a little air gap there right above the coils. Assuming the permeability of the material is 50 times mu 0 and all branches have a cross-sectional area of 10 square centimeters. And we're given the lengths of these guys. The gap is 1 centimeter, shown over here. Then the vertical distance is 10 centimeters, and then each horizontal segment there is 10 centimeters, and the number of turns here is 400. Now, if you did watch the previous two examples, magnetic circuits 1 and 2, this problem is a little bit different than those. In the previous examples, we needed a magnetization curve, or a BH curve. Here, we don't have that curve. We're not told what type of material it is. Instead, we're given its permeability. So you need one of those two things. You need the curve or you need the permeability. And the idea is that in ferromagnetic materials, the the BH relationship is not linear. Okay, it looks something like this, where if this is B and this is H, and so so the mu actually changes. So what they're telling you here is that at this particular operating point, the maybe we're operating here, the the slope of the tangent is 50 mu 0. So and in linear materials, non-ferromagnetic materials, this is just a line, and so that's why we never really talked about a BH curve before ferromagnetic materials. So if you don't quite understand that, I think that's okay. Just know that you need either the magnetization curve, in which case you find the point that you're operating at, or you need mu of the material. So you need one of the others, or one of those two things. So the first two examples we were given the BH curve, and in this third example we're given the magnetic permeability of the material. So we need one of those two things. Moving on. So the first thing I'm going to do here is realize that, oh, this I can use electrical circuits for, which is so cool. And so the curves, or the coils around the material there, produce a magnetic potential. So I'm going to start there. Here's my magnetic potential Vm, okay? And I'm going to just draw my circuit in the same geometry as the magnetic system. So right away then, right above that, spatially, I have a gap, and so I'm going to put the reluctance of the gap right there. Now, there are a few ways to do the remaining parts of this, but I'm going to do it this way because I think it's most clear, although it might not be most efficient. Then I have a segment from 5 to 3, so I'm going to put reluctance 5 to 3, and that's material. That's this material whose permeability is 50 mu 0. And then I have a segment going this way, and so I'm going to put reluctance 3, 4, like that, and I'm going to put then I have reluctance 4, 1, right? So I'm going to put that, I can put that here, 4, 1, like this, and then when I come up I have reluctance 1, 6, so I'll put that here, 1, 6. And you might ask, and students have asked me this in the past, well, can't I just consider segment 3, 4 and 4, 1 just to be one long segment, 1, 3, right? And yes, so series resistors add, so you can just add those two segments together and just put one reluctance there. So like I said, I think this is the most clear way of doing it, but it's not the most efficient way. So then I have kind of a symmetrical argument over here. I have reluctance 3, 2, right? And then I have, and I'll put it down here like I did the other one, reluctance 2, 1. So there's my magnetic circuit. Very cool. All right, so I've got my equivalent circuit, right? And what I can do is find the flux in the gap. So that would be, let me label that in my figure. That would be here. All right, and the way I do that is, of course, the integral of b dot ds in the gap. So I have, do I have b? Let's see. Yeah, I have b, right? That will produce a magnetic flux density of 1.5 Tesla in the gap. So that's b. And ds, I have the cross section of this thing is 10 square centimeters. And so I have b and I have s, and the b and ds are parallel with one another. So if you recall, the coils produce a b, or a flux density that's along the axis of the coils, up and down in the figure. And so that's exactly the normal to the cross section, is up and down. So b and ds are parallel, so this this integral of b dot ds, right, when those are parallel, this is a very easy integral. That's just b times s. So that is the flux through that air gap, b times s. All right, now I have, the current, if you will, through this middle branch. Now let me find some other circuit parameters. So let me get the reluctance of 5,3. So reluctance of 5,3. Well, how would I get that? Well, that is the length of segment 5,3 divided by mu of this material times the cross section of this material. So we have length 5,3. It is 10 minus 1, right, because 1 is a gap. So that would make 9, and then divided by 2 because of the symmetry. So it's actually 9/2 centimeters, L is. And then mu we know is 50 mu 0. And S is the cross-sectional area. So I'm not going to write all the numbers out just yet, but we have all of these things. And then I'm going to point out to you that due to symmetry, that's also equal to the 1/6 reluctance, because everything we just said about 5,3 we can say about 1/6, i.e. it has the same length and it's the same material. So we have those things. Now let's talk about the reluctance 3/2. So reluctance 3/2 we also can get, it's the length of 3/2, which is 10 centimeters, divided by mu, which is 50 mu 0, times its cross section, which we have also. So we have all of those numbers, and then I'll point out that due to symmetry, that's also equal to reluctance 3/4. Okay, and then similarly, reluctance 2/1 is the length of 2/1, which we have, divided by mu s. Okay, and then so we have all of those things, and then I'll point out that that's also equal to reluctance 4/1 due to symmetry. So we have all of that, and then finally, the reluctance of the gap is the length of the gap, which we have in the picture. It shows it over here, 1 centimeter, divided by mu 0 for air times s, right? So we have all of that, right? So we have all of the reluctances, and we have the flux in the middle branch. So let's get the total reluctance. And again, I love circuits, and so this is really a cool thing that we can identify series and parallel combinations of reluctance now to get the equivalent reluctance. So now I can say that yes, 3/4 and 4/1 are in series, so I can add them. 3/4 plus 4/1, right? And then that actually is in parallel with the series combination 3/2 and 2/1. Okay, so I've got that, and then once I combine those 4 resistors like I have, then those are in series with the I said resistors, reluctances. Those are in series with the remaining 2 reluctances. So think about your circuit theory class. Okay, plus the gap. So actually there are 3 remaining. See, in the middle branch, all three of those reluctances are in series, and so that adds to the combination of the other four, like that. Okay, so I plug in all of those numbers. So I will let you work out those calculations on your own. Okay, but take into account that square centimeters is 10 to the minus fourth square meters, 10 to the minus 4, because 1 centimeter is 10 to the minus 2, and this is squaring. So 10 to the minus 4, mu 0, of course, is 4 pi times 10 to the minus 7, and so on. So when you plug in all of those numbers and when you compute the parallel combinations and so forth, you get 70 over 50, and actually we're gonna keep it mu 0s like this, times 10 to the minus 2, and this is amp turns over Weber. That's reluctance. Amp turns over Weber. So each one of these terms has a mu 0s in the denominator. So we're just going to keep it like that for now. Okay, so yeah, we're going to move on there. So we've got the equivalent reluctance, and so here's the neat thing. So now I can use my circuit theory, right, and I can redraw this figure like this. So I've got my total reluctance, or my total magnetic potential, and then the equivalent reluctance, and then I know what the current is, right? The current, the flux. The flux is still this flux that we calculated, B times S, through the gap. So here's my equivalent circuit. All right, perfect. So now we can apply Ohm's law, and we can say that Vm equals the flux through the gap times the equivalent reluctance, like that. And so this would be 1.5, right? That's B times S. And then this would be 74 over 50 mu 0 times 10 to the minus second. Okay, and then that's in amp turns, right? Amp turns is the unit for magnetic potential, and so that comes out to be 17,666.2 amp turns. So I want to know how much current, and I've got the number of turns as 400. So remember that the thing that's causing this potential is the number of turns. It's the linkage, right? The number of turns, and each turn has a current I, and so now I set that equal to my 17,662.2, and I get the number of, or the current is 17,666.2 divided by 400. And you can see that with the units very clearly. The numerator was amp turns, and then if I divide by the number of turns, 400, then I get amps. That's cool too. It's neat. And then so I get 44.2 amps. And that is the amount of current that this thing needs to have.